We're going to talk about chemical equilibrium today. In the previous chapter, we talked about kinetics, and that is the study of reaction rates and the factors that affect them. With chemical equilibrium, what you are going to see is that when the rate of the forward and reverse reactions are the same, you have achieved a state of chemical equilibrium. So this will be the first time that you're looking at chemical reactions that run both forward and in reverse. So we're going to be taking a look at reversible reactions. Today you're going to learn how to write KEQ expressions, which is very, very easy, how to solve them, how to interpret them, how to calculate concentrations of substances at equilibrium. And then next time we'll get into Le Chatelier's principle, which is far worse than it sounds. Once you're shown how to do it, I think you'll find it to be pretty easy. And our lab, which is truly one of the best labs of the year, illustrates Le Chatelier's principle in action, where you start out with a pink solution, you add very strong acid to it, you get a blue solution, you cool it off, you get a pink solution, and the reaction just keeps running back and forth from pink to blue. And you'll see what happens at equilibrium. If you know your primary, secondary, and tertiary colors, you'll be able to make these predictions. And if you're not into your little colors, don't worry, we'll fix it for you. So today we're going to introduce chemical equilibrium, learn how to write equilibrium constant expressions, and here we go. So, second to last chapter for the year, we're going to be talking about chemical equilibrium. Previously, we have talked about chemical reactions, and there is quite a bit of information that you've already learned this year. For example, magnesium and hydrochloric acid are your reactants. They react to form products, magnesium chloride and hydrogen gas. And what you're seeing here is a rearrangement of atoms from left to right. But most importantly for our purposes here, you're seeing that forward arrow, which indicates reacts to form or yields. And in all the chemical reactions you've looked at this year, you've only seen that forward reaction, indicating that the reaction goes in the forward direction. All of the limiting reagent is used up, and it determines how much product you generate. And there are a number of ways to show that reactions go in the forward direction to completion. Conductivity we'll talk a little bit about in our acid-base chapter after this one. You've run some precipitation reactions where you mix two clear solutions and you got chunks in there of different colors. In this case, silver chloride would be a white precipitate. You would see white chunks. Down here you see a lot of rusting due to oxidation. So iron and oxygen gas react to form iron 3 oxide, which is rust. And in each of these reactions, you have an arrow only in the forward direction, indicating that the reaction runs forward and goes to completion, where the limiting reagent is used up entirely and determines how much product that you make. However, what you're going to see in this chapter is that not all chemical reactions go to completion. Sometimes you have reactants left over. Sometimes you generate products and they can react to reform reactants. Essentially, the reaction can go forward and backward. And when you have this, you have what's known as a reversible reaction. And this is what's shown here. Nitrogen dioxide, which is a brown gas, reacts to form dinitrogen tetroxide, which is a colorless or clear gas. You will also see that this colorless or clear gas will break apart to reform the brown nitrogen dioxide. So the reaction can run forward and it can run in reverse. And nobody wants to write all of that out, so instead we represent this reversible reaction with this double arrowhead shown here. And when the solutions are colored, you can see what substance you have, whether it's reactant or product. And this can be affected by changing concentration, changing pressure, changing volume, changing temperature. And that's something we'll be taking a look at in the lab. And so, for example, in this video shown here, you you are going to run that reaction.
We start this experiment with 3 tubes containing red-brown NO2 and colorless N2O4 in equilibrium.
So when you have a state of equilibrium, you will see that the rate of the forward and reverse reactions are equal. So at equilibrium, you have a blending, if you will, of color, so you'll have a situation where you have light brown. In the lab that you're going to be running, you will start with a pink solution, you'll add acid, you'll generate a blue solution. What color does red and blue or pink and blue make? Purple. So at equilibrium, you'll see a purple color, and by changing the temperature, you'll see that we can shift equilibrium either forward or reverse. And there's a lot of different color schemes you can look at. So right now you've got an equilibrium situation, so it'll be light brown, and we're going to take a look at what happens when you increase or decrease temperature.
First, 1 tube is placed in hot water. A second tube is placed in cold ice water. After a few moments, we note that the tube in hot water has darkened in color. It now contains more brown NO2 than the tube which we kept at room temperature. The tube in ice water has less brown NO2 in it. It is much paler because the equilibrium has shifted to favor the formation of colorless N2O4.
And so you can see in the warm water you've got the deep brown, and in the ice water it's very light. And so the reaction can run both in the forward and reverse direction. These types of reactions are reversible. Both nitrogen dioxide and dinitrogen tetroxide will react continually. When the reactions occur at equal rates but in opposite directions, that is, when the rate of the forward and reverse reactions are equal, we have a state of chemical equilibrium. And this is a dynamic process, not static. With dynamic, for example, if you were watching a beehive, the bees would go in, some would come out, some would go in, some would come out. It's not like the bee movie where they go and sit on the couch and watch TV, but rather a dynamic process, so in and out. You go to a ball game, you go to a concert, you'll see not everybody sitting in their seat. Some people are getting refreshments, some people are going to the bathroom, buying souvenirs, etc. So a very dynamic process. Think about the parking lot in the morning, coming in, going out, coming in, going out. Very dynamic process, not static. When the rates of the forward and reverse reactions are the same, then we have a state of chemical equilibrium. And we can look at what happens to the concentration of reactants and products as equilibrium is approached. So again, same reaction we looked at previously. Nitrogen dioxide will be your reactant on the left, dinitrogen tetroxide will be your product on the right. Nitrogen dioxide is a reactant, so its concentration will decrease over time, and then you're going to see this plateau. So it's not used up entirely. Dinitrogen tetroxide, a product, will increase in concentration over time until it plateaus. When they're both plateauing, you've got equilibrium, and this is TC, that critical time at which equilibrium is established. So when it plateaus, you've got it. And I'm showing you these graphs this year. You'll probably see them in college chem. You'll definitely see them in AP chem. But the more you see, the more you're likely to remember. I'm not going to assess you on this per se, but you do want to understand that reactants get consumed. Their concentrations will decrease over time. Products get generated. Their concentrations will increase over time. Shown here, you've got the formation of ammonia in a reversible fashion from nitrogen and hydrogen gas. And again, why do these concentrations increase? Why does this one increase over time, whereas these two decrease?
One's a reactant, one's a product.
Absolutely. So you've got your reactants and your products. Why would the concentration of hydrogen gas be greater than that of nitrogen gas at equilibrium? Absolutely. Mole ratio from balanced chemical equation is 3 to 1, stoichiometric coefficients. So these are all things that you've learned about, and it's just a matter of putting it together. This is the critical time at which equilibrium is established. One of the best examples of a reversible reaction is what goes on in your car battery. When you turn your car on, you've got lead 4 oxide, and sulfuric acid in the battery reacting to form lead 2 sulfate and water. Is this an endo or exothermic reaction? Exo, because energy's on the right side. Now, if for some reason you try and start your engine and it won't start, you may need to jump start. Don't jump start unless you know how to do it. You're better off calling someone in. They don't recommend that much jump starting anymore. It can be very detrimental to the vehicle you're jump starting it from. But in any event, when you jump start, you run the reaction in reverse. You force it in the reverse direction, so then it catches and runs in the forward direction, so at least you can get where you need to go if your battery is dead. I already mentioned some of those other dynamic processes. Typically, we look at concentration of reactants or products over time, but you can look at changes in masses. You can look at temperature. In the lab, we're going to be doing colorimetric type assays, so they won't be quantitative, but rather qualitative. You also can look at conductivity. But for the most part, we're going to look at concentration of reactants or products. You also can look at pressure if you have gases. We are going to learn how to write equilibrium constants today. It's very, very simple. We're going to learn how to calculate them, how to interpret them. I think all of that will be pretty straightforward to you. I think the only tricky part will be calculating concentrations just in regard to mastering calculator use and simple math operations that you've probably seen in Algebra 1 and perhaps Algebra 2. So with the equilibrium constant, you can establish a relationship between concentrations of reactants and concentration of products using what's known as an equilibrium constant. K for constant, EQ, not EG, EQ for equilibrium. For example, you've seen this generic reaction written previously where the lowercase letters represent stoichiometric coefficients and the uppercase letters represent reactants or products. An equilibrium constant expression is KEQ, which you must write, is equal to concentration of products raised to their coefficients. And it's the product of the products. You're multiplying these, not adding. Be careful. There's always one student who starts adding like crazy. It makes a big mess. Over reactant concentrations raised to their coefficients. You must have concentration brackets here. Products go on top. Just remember, pot, products on top. Products in the numerator, reactants in the denominator, and you'll be successful here.
So what it's raised to is its coefficient. How would you measure the concentration?
So in terms of writing them, you'll write it as such, and you are absolutely correct, where this exponent here is the stoichiometric coefficient shown here. In regard to writing them, to solve KEQ, you'll be given the concentrations, which you'll plug in and you'll solve. But you are correct in that the stoichiometric coefficients become the exponents. And just be careful, it's the product of the product concentrations, it's the product of the reactant concentrations. Products in the numerator, reactants in the denominator. So if you had this equilibrium reaction shown here, what's happening is initially these two are reacting to form product. As you use more reactant up, the rate at which the forward reaction occurs is going to decrease because you're going to have fewer particles in there. The likelihood of an effective collision will decrease. Then as you generate this substance, this is more apt to break apart to reform reactants. Your equilibrium constant expression would look like this: concentration of product over concentration of reactants. We can solve for KEQ. You will see that KEQ values are temperature dependent. If you change temperature, you will change the value of KEQ, and we'll talk about that next time. But you'll see that temperature is the only factor that alters the value of KEQ. And when you're writing KEQ expressions, you only put gases or aqueous substances in KEQ expressions. No solids, no liquids. Let's take a look. We're going to write KEQ expressions for the following equations. We'll take it one at a time. I'm going to rewrite the balanced equation on my paper. You already have it in your notes, so you don't need to rewrite it. We've got 2 moles of sulfur dioxide gas reacting with oxygen gas. Reversible reaction should generate 2 moles of sulfur trioxide gas. When we write our KEQ expression, don't forget to write the KEQ. That's an E. Product concentration over reactant concentration, each concentration raised to the stoichiometric coefficient. And that is an equilibrium constant expression. You only put gases or aqueous substances in KEQ expressions. In the next one, we have 4 moles of hydrogen chloride gas reacting with oxygen gas to generate 2 moles of chlorine gas and 2 moles of water in the gaseous state. So how would we write the KEQ expression for this one? What would go in the numerator? Go ahead.
Chlorine raised to the 2nd power times water raised to the 2nd power. Over HCl to the 4th power times oxygen.
Perfect. And you just need the brackets to represent concentration. Remember, brackets like that indicate concentration. The third one's a little bit trickier, but I know that you're going to pay attention to the state of matter and you won't make a careless error. So if you write the KEQ expression here, what would you write?
Put on top of brackets and then CO squared, and then on the bottom it would be brackets CO2. That's it.
Did you forget something?
No.
No, because this is a
Solid.
and you don't put solids or liquids in KEQ expressions.
You just ignore it?
It's not in an equilibrium constant expression because its concentration won't change. I knew you were going to do it right. I wanted you to explain it. All right, the last one looks really funky, but I gave it to you because this reaction is similar to the one that we're going to run in the lab, so I didn't want that to be a surprise to you. You've got complex ions here, so they really look a little crazy. Those charges are important in regard to what the substance is. And when you have an ion, you have an aqueous substance. So take a minute to write the KEQ expression for that one. It's at the top of the screen. And let's see if you did this one correctly. And check to see that you've written it correctly, and hopefully you were very meticulous in regard to water in the liquid state. Yes, yes? Easy peasy?
We have to put the charges?
Yes. Well, charges in here, when you balance an equation, not only do you balance for atom, but you also balance for charge. So on the left side of the equation, you have a net 2 minus from here. And on the right side of the equation, you have 2 plus 4 minuses for a net 2 minus here. So the charge has to cancel out overall, otherwise you've made a little boo-boo. That'll be important in net ionic equations. All right, so you know how to write KEQ expressions, and now if given concentrations, the question will be, can you calculate the value of KEQ? And this is really pretty simple. You want to simply put the concentrations in. Make sure you know how to use your calculator. If you don't have one, you're welcome to borrow. Just make sure that the calculator you're comfortable with is the one that you use on the quiz. So the next thing we're going to do is we're going to calculate KEQ from concentrations. We are not going to have a unit for KEQ because each equation can have a different unit of KEQ, and it becomes so tricky that we simply do not use units for KEQ. So KEQ will be a number, not a quantity with a unit. Use the corresponding chemical equations below and the concentrations of reactants and products provided to calculate the value of KEQ. And we'll take a look at this first example. Whenever you're doing these types of problems, you always want to write the KEQ expression. So in the first one, we've already written this KEQ expression. It was one of our initial examples. We're generating 2 moles of hydrogen iodide gas from hydrogen and iodine in the vapor state. And when you're trying to calculate KEQ, the first thing you always want to do is write your KEQ expression. Again, product concentration in the numerator, reactant concentration in the denominator. Once you set this up, you can essentially just plug and chug away. They give you the concentration of hydrogen iodide at 0.0173 molar. You will need to square that because of the coefficient of 2. They give you the concentration of hydrogen gas at 9.1 times 10 to the negative 3 molar, and the concentration of iodine at 5.9 times 10 to the negative 4 molar. In your calculator, the only parentheses you need, unless you have that multi-view, will be the ones in orange. Make sure that you can calculator punch with ease. Don't forget to square the numerator. And KEQ is equal to 56 in 2 sig figs. So again, when asked to calculate KEQ, you want to write the KEQ expression. You're going to plug those quantities in and solve. In your calculator, you are punching, if you're having trouble, 0.0173 squared divided by open parentheses 9.1 EE negative 3 times 5.9 EE negative 4 close equals. Are you getting the right answer? Yes, yes? No. There are no units for KEQ, and in this case they cancel anyway because you would have molar squared over molar times molar, so they would cancel. So we don't use units for KEQ. Makes it easier. But if you're asked to calculate concentration, which you will be in the next section, then you indicate units of molarity. All right, let's take a look at number 2. You want to do it together or you want to try it? You want to try it or you want to do it together? Try? All right, go for it for number 2. And again, always start by writing the KEQ expression. How did we do? That's what I got.
What?
Okay, before you what, and go nuts, look at the setup. Do you have the right KEQ? Did you plug in properly? Calculator entry, 0.0155 squared, divided by open parentheses 8.3 times 10 to the negative 3 times 9.1 times 10 to the negative 3. Don't forget to cube that one because of the coefficient of 3 in front of the hydrogen. You get that? You want 2 sig figs, so you can take either of those. You had a question? All right, so you know how to write a KEQ expression. You know how to solve for KEQ. We want to be able to interpret KEQ, and a lot of this is written out for you. I'd like to try a simpler approach. I don't really like to memorize. I like to understand. So we know that KEQ is equal to concentration of products over concentration of reactants. If the concentration of products is greater than the concentration of reactants, that means this quantity is greater than this. Will KEQ be greater than, equal to, or less than 1? Greater. And if we consider reactant being converted to product, or product reforming reactant, if product concentration is greater, that means that the forward reaction rate must be faster. So it indicates that the forward reaction is favored. So if product concentration is greater than reactant concentration, KEQ will be greater than 1 because the forward reaction is favored. On the flip side, if reactant concentration is greater than product concentration, now we're saying the denominator is larger, so KEQ will be less than 1. So in this instance, the reverse reaction is favored because your product concentration will be greater than that of the reactant. So when KEQ is less than 1, this is because the reverse reaction is favored. And just as an aside, to bring back our thermo chapter, if the forward reaction is favored and you've got thermodynamic favorability, will delta G be negative or positive? Negative. So with a KEQ greater than 1, delta G would be less than 0. Now when you've got equal product and reactant concentrations, KEQ would be what? No, no, no. would be 1. 5 over 5, for example, would be 1. So at equilibrium, where you've got equal concentrations, KEQ will be 1. Delta G then would be 0 there in that case. That's getting a little too advanced. For your purposes right here, for example, look at the KEQ we calculated here. Would the forward or reverse reaction be favored? It's not a yes or no question. If KEQ is 38,000, would the forward or reverse reaction be favored? Forward. So in this one, the forward reaction is favored because KEQ is greater than 1. So on your quiz, I'll have you write a KEQ expression, I'll have you solve it, and then I'll ask, is the forward or reverse reaction favored and why? And you would indicate in this one the forward reaction is favored because KEQ is greater than 1. What about on the previous problem we did where we had a KEQ of 56? Would the forward or reverse reaction be favored? Forward because KEQ is greater than 1. Let's say, for example, that you had a KEQ value of 3.0 times 10 to the negative 4. Would the forward or reverse reaction be favored? Reverse. So here the reverse reaction is favored because KEQ is less than 1. So once you calculate your KEQ, I'll ask you to interpret it, and I won't say interpret it. I'll say is KEQ greater than, less than, or equal to 1? Explain why. So here, you would say that the reverse reaction is favored because the KEQ is less than 1. Now don't be confused. KEQs can, of course, not be negative. So if it's less than 1, it is greater than 0. It's just to a negative exponent. So you know how to write KEQ expressions. You know how to solve KEQ expressions. And you know how to interpret them. And the last thing we want to look at today is if you are given KEQ and 2 concentrations, can you get the missing equilibrium concentration? Not difficult. Be very meticulous with your setup. You need to be able to manipulate variables and use your calculator, and it should be very straightforward. So that's what we're going to look at in the next section here. We're going to walk through several problems together, and then you'll have the opportunity to do some practice problems. In number 5, it says the concentration of reactants or products can be calculated when a value of KEQ is provided, as well as some concentrations of substances. For example, use the chemical equation and information provided to calculate the concentration of the valueless substance. Same reaction we've looked at a few times. Concentrations of reactants given. We want to know the concentration of hydrogen iodide gas. The KEQ is given. Anytime you're doing these types of problems, your approach will be similar to what you've seen previously. You want to write the KEQ expression. So what we're looking at in this problem, when you're asked to calculate the concentration, your approach will still be to write the KEQ expression that we've talked about already. You've got hydrogen iodide over hydrogen gas and iodide gas. or iodine gas. And we want to solve for concentration of hydrogen iodide. I am going to cross multiply. I'm going to have hydrogen iodide concentration squared is equal to KEQ times hydrogen gas times iodine. Now I want to know the concentration of hydrogen iodide, not hydrogen iodide squared. So what times 2 is equal to 1? A half, right?
2.
So you can either take all of this to the 1/2 or you can just square root both sides.
You can just square root it at the end.
You can if you want to. Just don't forget. So your concentration of hydrogen iodide is going to be the square root of KEQ, which is given as 56. Hydrogen gas has a concentration of 0.0091 molar. Concentration of iodine vapor, 5.9 times 10 to the negative 4 molar. Plug it in and take the square root. And the concentration of hydrogen iodide is 0.017, capital M, molarity or molar for concentration. So when solving for the concentration, write the KEQ expression. Isolate the variable that you want to solve for. Make sure it's to the first power. Plug in and solve. And you can always go back and check, because you could plug this in here, square it, and divide it by those and see if you get your KEQ out. Let's do another one. For number 2, the first thing we always do is we write the KEQ expression. Again, products of gases and aqueous substances in the numerator. We've got chlorine gas to the second power, water vapor to the second power, hydrogen chloride gas to the fourth power, oxygen. Here, reactants are in the denominator, products are in the numerator. And I want to solve for oxygen. Early in the year, we talked about how you can interchange a numerator on one side of the equation with a denominator on the other side of the equation. If you don't feel comfortable with it or you don't trust it, by all means cross multiply and solve. You'd have to cross multiply, you'd have to divide by these two on both sides. And what you would get out would be concentration of oxygen is equal to, same numerator, and that essentially is the same as interchanging the numerator on one side of the equation with the denominator on the other side. Be careful, don't start interchanging numerators. That's a no-no. Only the numerator on one side with the denominator on the other side. Once you do that, it really becomes a plug and chug situation. It's actually very simple once you've set it up properly. Chlorine, concentration of 1.5 times 10 to the negative 3 molar squared. Water vapor, 0.345 molar squared. HCl, 0.555 molar to the fourth. KEQ, 1.0 times 10 to the negative 2. Hey, with that KEQ, would the forward or reverse reaction be favored? Reverse, because that KEQ is less than 1. In your calculator, the only parentheses you need are the ones in orange unless you have the multi-view, and I would not use that one. You're going to make a calculator error. And again, you can always go back and check your answer. You can multiply that by HCl to the fourth, flip it, multiply out the numerator, and you should get the KEQ. If you don't, you've made a calculation error. So when I do these types of problems, I always write the KEQ expression. I manipulate it, so I'm solving for the variable in question. Plug and chug, solve. Also remember that if you're solving for concentration, your unit is capital M for molarity, moles per liter. Let's do another one, and then we'll see if you can try some, and you will be on your way. Number 3 is a little tricky on multiple levels. In number 3, look at your equation. Which substance will not be included in the equilibrium constant expression? H2O, because it is a liquid. So what you want to do is you want to write the KEQ expression. So the first thing you're going to do in number 3 is write the KEQ expression. Products in the numerator. Why am I taking chloride ion to the 4th power? Coefficient? So there's my KEQ expression. Now what do I want to solve for?
The chloride ion.
Chloride ion. Now we've got to get that by itself, and that's in the numerator. So I'm going to go ahead and cross multiply. I'm going to have KEQ times what was in the denominator. Here's my numerator. And what will I do next? Divide by that. So this is just baby algebra. but this is to the 4th power, and I want it to the 1st power. So 4 times what fraction is 1? 1/4. So to get this to the 1st power, I have to take this to the 1/4 root. And in your calculator, you can do arrow up, open parentheses, 1 divided by 4, or arrow up 0.25, whatever's easier for you. So now we're going to plug in and solve. KEQ is 2.3 times 10 to the 3rd power, 0.40 molar, 0.75 molar, and we're going to take this whole thing to the 1/4 power. And see if you got what I got.
I have a question.
Okay.
Why do you have to for the chloride ion? Why do you have to make the power 1?
Because you want to solve for the concentration of chloride ion, not chloride ion to the 4th power. So you always want to solve for the concentration to the 1st power. So if this were to the 6th power, you would take this to the 1/6 power. If it was to the 5th power, you'd take it to the 1/5. And again, you can go back and check your answer and see if you get the KEQ out. That will show you whether you've done it correctly. What I find is kids forget to do this last step, so be careful there. It's not hard, but you have to be very meticulous with your work. Write the KEQ expression, solve for what you want in terms of it being a variable to the 1st power, plug in, calculate. Try and do number 4. See if you can do it. Try. Anybody have an answer for number 4? What do you got?
2.3.
Not what I got.
0.87.
I got 0.87. Well, what you want to check in number 4, first see if you've manipulated it properly. Do you have it to the correct exponent? Did you plug in properly? Is it just a calculation issue? Because we can work on that in your calculator.
I plugged it in like that.
So that's a problem with variable manipulation. Again, if you're not comfortable interchanging a numerator and a denominator, cross multiply and then divide by those so that you isolate this by itself. So that's the answer to number 4. Who's ready for 5? Not yet? All right, but see, don't pout. Take a look. Did you manipulate properly?
Yeah.
Okay. Did you plug properly?
Yeah.
Okay, so it's a calculation thing. Bring your calculator up. I'm going to reveal the answer to 5. Don't look up till you're done. I just want to try and cut the videotape. Here's the answer to 5. This is the accompanying classwork, which I ask that you have done for Friday. I will go over anything you need in 4 or 5. Again, we've learned how to write KEQ expressions, solve them, interpret them, and solve for concentration of a substance. Next time we're going to take a look at stresses that affect equilibrium and how the system responds to at least partially undo the stress you've applied.